Lambourne to give us time travel.
Okay, well, thank you. It's a great pleasure to be here, of course, and to have this opportunity to talk to you. I love talking about time travel because I think it's great fun, but I'm also going to argue that there's a serious reason to be interested in it scientifically. I should reassure you, despite my interest in science fiction and enthusiasm for time travel, I am a real physicist, not a crazy person. But I like giving talks on all sorts of things that address the edges of physics. So I have another talk all about faster than light objects and stuff like that. But time travel, I think, is a nice one because it's full of physics. And as you can see, I'm planning something in a sense rather conventional. I shall start off by saying a few words about what is time. Not very much, because I don't know the answer to that. That's why I've been used it as a physicist all my life. I shall ask if time is a puzzle. And usually when I don't know the answer to a question, I resort to giving other people's answers to it. So you'll see the views of some others. I'll talk about time travel and its paradoxes, why basically we don't believe in time travel. And then I'm going to talk about all the ways in which physics might or might not permit time travel. So time travel in Newtonian physics, special relativity, general relativity, quantum physics. I'll finish off by even going a little bit beyond conventional science just for fun at the end, provided I have time. I should explain that I developed this talk originally as a presentation at the Edinburgh Science Festival, which is an annual event in the UK, and I used to be involved in helping to organise the scientific side of the festival. But then I enjoyed the talk myself so much that I thought, well, I'll give this in a few other places, and I started giving it to the UK Institute of Physics groups around the country. So I've given it on a number of occasions, but I feel free to change what's in it every time anyway. Okay, oh sorry, I should have said, just to make sure that everybody is up to speed on time travel technology. Does everybody recognise these two time machines? I'm glad to see lots of nods. Right, there's Carl Sagan, who, because he was a TV presenter as well as a scientist, had the fun of sitting in the H.G. Wells time machine from the 1960s film. And of course, Doctor Who's police telephone box. Telephone boxes like that. I was a child, I can remember the first episode of Doctor Who. I want a bit of respect for that. But when I was a child, police boxes like this were to be seen everywhere on the streets of London. So it was a great joke at the time that Doctor Who went around in one of those things. But of course, to the general public, they were not really very accessible. And so the idea that they might all secretly be time machines was a wonderful thought. Okay. As always, I want to start with the views of much smarter people than me who might be able to throw some light on what time is. And Aristotle, always good for a beginning, if not for a laugh, says there is no time without change. Time is really something that we humans have invented in order to account for the fact that things change around us. And we shouldn't forget that time is a human invention at the end of the day. We've come to kind of think of it as a pretty absolute thing in physics, and we'd be hard-pressed to get rid of it. It's a great problem to decide what to do without it. Philosophers have enormous discussions about what time really is, so they don't know either. But it is our invention, and I've certainly gone to seminars through my career where people have argued that time is one of the things, and this isn't meant as a joke, but time is one of the things slowing physics down, and that if we got rid of the concept of time and replaced it with something else, we'd be able to make progress much more rapidly. I'm tempted to just say I leave the rest of that seminar as an exercise for the listener. But I will say that one of the people who argued in that way was very keen on this idea of entanglement in quantum physics, but also in a straightforward mechanical way. And he was arguing that we would do much better to come up with some idea about the increasing complexity of systems, might or might not have something to do with entropy, but that was really the way in which we should aim to replace time. Other people have argued that in different phases of the universe, in the Big Bang, for instance, very early on, before there were any atoms around and everything was interacting strongly, timescales were much shorter, and perhaps we should have had a different concept of time based on strong interaction rates for what we meant by time at an early phase in the expansion of the universe. And the same argument would apply later. The most interesting argument along those lines recently, I think, has come from Roger Penrose in his book Cycles of Time, where he actually argues that maybe what happens in the very, very distant future is that the universe effectively forgets how long it's been around and how big it is, all scales disappear, and then a new universe is born from our universe simply because our universe has, as it were, forgotten what the scale of anything is, physically. I think that's a rather interesting idea. There's a lot more to that. He wrote an entire book about that. St. Augustine always quoted, what then is time? I know well enough what it is, provided that nobody asks me. But when I am asked what it is and I try to explain, I am baffled. Well, a lot of students have that feeling in exams. They know exactly what things are until we ask them the question, and then suddenly they can't remember what they are anymore. Newton, absolute, true, and mathematical time flows uniformly without relation to anything external. Now, that's the basic picture of time that you're given in much of the physics that you study, certainly in classical physics up to Einstein's developments. And I'll come back to that in a moment. And then Einstein, just for a contrast, it's not absolute. Time, according to Einstein, is relative, not absolute. It's a coordinate that allows an observer to separate events that happen at the same place. And then a very typically Einsteinian touch. You know, how do you actually measure time? It's what clocks measure. If I've got a clock that goes tick, 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 that's what time is. Yeah, I'm assuming it's a properly made ideal clock and so on. So a whole range of views there, which are interesting, but I'm not convinced they're all that enlightening. And then the anonymous one that I've always liked, time, it's just one damn thing after another. And everybody who gets harassed to prepare stuff knows exactly that feeling. Okay, well, that's what time is or may be. Let me just clarify the absolute versus relative argument, since that's of great importance to what follows, and it's central, of course, to relativity. Now, the Newtonian view is very simple. In the Newtonian view, we have a concept of the whole of space, which I'm representing by a two-dimensional sheet, and of course it's really three-dimensional in the Newtonian view, but I can't draw a diagram that shows it as three-dimensional. So this sheet represents the whole of three-dimensional space at one particular instant of time, which I will call t1. And at the next instant of time, t2, or sorry, at a later instant of time, t2, I have again the whole of three-dimensional space. t3, the whole of space. t4, the whole of space, and so on. And so what I have is really an infinite number of sheets like this, each one corresponding to a particular instant of time, each representing the whole of space. And Newton's idea is that time is absolute, that's to say all observers agree on what time is. If they've got differently regulated clocks, i.e. clocks that tick at different speeds, or if they've got a watch where somebody's watch is 5 minutes faster than everybody else's, well, they need to alter the rate at which their watch ticks, or they need to alter the time at which they start it from. Basically, time is capable of being agreed about by all observers. That's the Newtonian view of absolute time. And that makes good sense. You can imagine drawing a little diagram here showing the position of some things. That's called the universe. And you can imagine drawing a very similar diagram here, but with everything moved very slightly, and that's the universe at a slightly later time. And you can make sort of flick book cartoons. I don't know if that means things to people here, but certainly when I was a kid, there used to be little cartoon booklets, all with slightly different pictures, and you get an impression of a movie just by flipping the book. I've even seen physics textbooks that try to do that with the corners of the pages. Okay, so this is Newtonian absolute time. We would call it a foliation of space and time, where time is absolute and agreed by all observers. Now, the relativistic view, the special relativistic view at least, of Einstein is very different. In the Einsteinian view, according to special relativity, we have what's sometimes called the block universe, a four-dimensional structure. Again, I can't draw four-dimensionally, so you've just got a two-dimensional representation of a three-dimensional thing which is trying to stand in the place of a four-dimensional thing. But you get the basic idea. And in Einstein's block universe, the idea is that time for a particular observer is represented by some particular direction in this four-dimensional space-time. So time is again one-dimensional, but an observer will have associated a particular time. By an observer, I really mean an observer who is using a particular, in relativistic language, a frame of reference, a particular frame of reference. So a particular frame of reference is allocated to a particular observer, and it defines a particular direction as the time direction in this four-dimensional space-time. A different observer, and in special relativity a different inertial observer, who would be moving at constant uniform velocity relative to the first observer, experiences exactly the same four-dimensional universe, but expresses it differently in terms of space and time. So to the second observer, observer B, Observers B measurements reveal that time is some other direction in this four-dimensional universe. And to observer A, all of space at a given time is in a sense what's called a hyperplane in this universe, some plane drawn at right angles to the time direction. To observer B, the whole of space at some particular time is also a meaningful concept, but the whole of space at a different time implies a plane at right angles to observer's B time direction. And so what is space at a particular instant according to observer A is not space at a particular instant according to observer B. Not only, I've drawn those two planes separately, but even if I were to choose deliberately, as it were, the same time, the planes would be differently orientated. So the points in one observer that make up space for one observer, A, at a certain time, are different from the points, we would call them events in the language of relativity, in the same universe that make up space at a particular time for the second observer. Now, you're probably already very familiar with the mathematics behind this diagram, even though you may never have seen the diagram before, because the mathematics behind that is the Lorentz Transformations. Has everybody seen the Lorentz Transformations? What do the Lorentz Transformations do? Many students have a kind of vague notion that there's something about time and space, but actually they're very specific. Let me take two observers in a specified relative state of motion. Usually we use what's called a conventional motion between the two, a standard configuration of their frames of reference. For those two observers, where things essentially just differ by a velocity with which the observer moves, v, what will happen is that the set of coordinates x, y, z, and t that one observer, observer A, allocates to a specific event can be related to the set of coordinates that a different observer, moving with velocity v relative to the first, allocates to the same event. So what the Lorentz transformations really are a kind of dictionary for converting the coordinates of an event seen by an observer into a language, usually shown by primes in the relativity examples, used by the other observer. Now, I guess you've all seen that, like x prime, y prime, z prime, t prime. Don't think of them as vaguely coordinates of something or other. They are coordinates of an event seen by one observer and related to the same event as observed by, I used the word seen, which I should have said observed. Observers observe, seeing is a different process that involves time lags. But take the events as observed by one observer and relate them to coordinates of the same event as observed by another observer. Okay, so I hope everybody's happy with that, since I guess you all sort of know that, even if I'm using a slightly different language to what you're used to. Okay, great. And then when we go into general relativity, now I don't know how many of you have met general relativity already in your courses. Okay, so some have, some haven't. This is a very strong department in general relativity, so I'm not surprised. In many universities, people would not properly meet general relativity in their undergraduate degree, so I'm delighted that you have. I'm not going to write down the equations, don't worry. But what I'm going to do is to just chat about it. In general relativity, the idea is that the old Newtonian concept of a force of gravity is thrown away. There are no forces of gravity in general relativity. Instead, we have the notion of space-time curvature replacing that. Gravity becomes not a matter of forces, but a matter of space-time geometry. And what happens for observers in this curved universe that Einstein told us would be able to cope with a description of gravity is that essentially observers have a concept of time wherever you are in that universe, and you're living in such a curved space-time universe, so it's this universe. Wherever you are in that universe, you still have a concept of time. We all know perfectly well which direction is the time direction. It's the direction in which our hair gets greyer and so on, and if we're unlucky, eventually falls out. So there is a time direction. In some sense, there is a hyperplane at right angles to that, which represents space. It's not so easy to say it represents the whole of space because cosmic geometry is very complicated. But there is a time direction. And if I have two observers moving relative to one another in any one locality in a curved space-time, then on the small scale, special relativity still works even in a general relativistic universe. Locally, as they say, special relativity is true. So these are still like observers A and B on the last sheet, but the idea that you can apply that mapping between them to the whole universe essentially breaks down. So time and space is not only, time and correspondingly space is not only particularized to an observer in this case, but also to a location. And so our notion of time depends not only on how fast we move, but also in this curved space-time on what the local geometry of space-time is. And it's possible to conceive of places with such highly warped geometries like black holes and so on, where the whole concept of time runs into some difficulty. And indeed, at the heart of a black hole and singularity, the concept of time would certainly break down according to general relativity. Okay, so in general relativity, time is not only relative, but it also becomes to some extent local. There is time wherever you are, as long as you're not at a singularity or something like that, but it's not the same everywhere across the universe. Okay, well, is time a puzzle? Here are two views. Hilary Putnam, very famous American philosopher of science, who absolutely buys the Einsteinian view. I do not believe that there are any longer any philosophical problems about time. Philosophers still write books about time, but Putnam's very clear. There is only the physical problem of determining the exact physical geometry of the four-dimensional continuum that we inhabit. Pretty clear answer to the question. But not everybody agrees. Ian Barber, a well-known physicist in the UK, but a man of somewhat eccentric views, wrote an entire book about time. I now believe that time does not exist at all, and that motion itself is pure illusion. The idea that motion is illusion goes right back to the Greeks. I'm not going to discuss that, but that's just to show you the range of views that you can still get today. I'm not going to throw any light on that, because that's just, as it were, a disagreement between two people with philosophical views, and the problem with philosophy is, unless it becomes a physical question, it's very hard for physicists to resolve it, because you need some experimental, observational input to resolve those kind of conundrums. And I don't think we really have that for time. Now, time may not be a puzzle, but now certainly is. When I was a schoolboy, about 14 or 15, my physics teacher asked, this probably means he was desperate for something to do to fill an hour, so he got the entire class to write an essay on what is now. And I've never quite got over that experience, because I'm still seriously challenged by what is now. Now, all of us as physicists or physicists in training, we all know what now is, right? We live in a now moment. We experience now around us, and we all have a kind of interior feeling that the past is dead and fixed, and the future is unknown. And we won't know it until we experience it, until we live through it. And there are deep philosophical and even religious questions about whether or not we have free will. Is what's going to happen in the future preordained? Is it in some physical sense fixed, and it's just going to happen to us anyway? Or can we, by an act of will or some other exertion on our part, change the future? Many philosophers felt threatened by physical science and felt that the future was fixed and that there was no such thing as free will. And that's one of the reasons why many of them embraced quantum physics, even though they didn't understand it necessarily when it came along, because suddenly things seemed fuzzier, ill-determined, and suddenly it seemed like the future was a matter that we could influence again. Now, it's not at all clear, but if you think about the physics that you've been learning, it's rather worrying. We all know what we mean by the now moment, and in your equations and so on, you will often write down something like t, the time, and you'll even have sometimes t subscript now, or t0 or something to represent now, the current period of observation, or whatever. But if you think about the equations that you write down, now, in all of those equations, I think, will have had no special significance. It's just a time you chose to represent now. Now does not really feature in physics. If you look through the literature, you'll find papers with titles like The Physics of Now. But I certainly don't find them very illuminating, and they're full of very strange ideas, like using sentient robots or something. This is meant to be conventional physics to try to explain to us what now means. Now plays no central role in any of the physics equations that you use. Look at Newton's equations, look at Maxwell's equations for electricity and magnetism, look at the Schrödinger equation. You can always choose a time to represent now, but it's got no special status. That's the extraordinary thing about physics. Now has no special role in it. And that really is the case for physics. We have invariance under time translations. If you've met Noether's theorem yet, I don't know if any of you have, I see a couple of nods. When you meet Noether's theorem, then let me put it that way, what you'll find is that the conservation of energy is related to the symmetry under translation of time of physical laws. If physical laws were not translatable under time for closed systems, or isolated systems rather, would not conserve energy. So this time invariance, which is one of the reasons why we have no special significance attached to now, is something that vanishes if we try to give now a special significance. A widespread view amongst physicists, and that's my way of saying we don't all agree on this, but people who have thought about it often tell me that, whoops, sorry, let me just go back. Okay, that now is a matter of consciousness. Now this is a really good argument, because that means that a physical discussion of now must await the development of a more complete physical theory of consciousness. Now that could be a very long way away. I went along to the meeting of the New Zealand Institute of Physics last weekend, and there was a splendid talk by somebody from Australia, one of the plenary sessions, about attempts to form a field theory, what's called a mean field theory, which means something, I guess, to some of you who have done advanced physics already, and the rest of you will be encountering it during your studies. But to formulate a mean field theory of a system of neurons, to have a mean field theory of the brain, so that they can apply things like Feynman diagrams to working out brain states and see what perturbations do to the brain. Now, I think that's very exciting. But according to this view, it's the development of that kind of field at some stage in the future that will give us a theory of consciousness that will in turn give us some physical understanding of now, over and above simply setting a particular time equal to the now moment. But this is still a subject worthy of essays, and in my view the essays just need to get longer and longer and longer as time passes until we really crack this problem. Now is something that we as physicists should understand, but we don't at the present time. Okay, let me give you quickly the case against time travel, and then I'll give you some arguments for time travel. Exhibit 1, no known time travellers. Now, occasionally in your life you might meet people who claim to be time travellers. I don't think I have, actually. I've certainly met somebody who claimed to be a commander in the Syrian space fleet. But I think he did that. And I think many time travellers that you're likely to meet might fall into the same category. I'm full of praise for the students at MIT. This is no criticism of you, but I think it was a very smart move on their part, and I hope your physical society will consider not the same, but similar kinds of moves like this. The MIT students threw a party for time travellers. I think this is a splendid notion. They advertised as well as they could, this was a few years ago, but they advertised as well as they could that in a certain quadrangle at MIT there would be free wine and cheese for any time travellers who could turn up and establish that they really were time travellers. And they put it into some of the popular physics magazines in the hope that time travellers in the future would know that if they wanted to prove to humankind that time travel was possible, they should go to this particular place at MIT in Cambridge, Massachusetts, and prove that they were time travellers to the assembled physics students and their physics professors. And if they did that at MIT, we'd all have proof that time travellers existed. Now, I don't know the fate of those magazines in which they publish the news of the event. It may be there's some dreadful calamity, and that all the information about that gets destroyed in a year or two's time, and all the time travellers become abundant because of new developments in time travel technology in about 5 years' time, and just never know to go back to this event. Who knows? But none of them turned up on the day. The students, fortunately, had arranged for one or two eminent MIT professors to have lectures on hand just to fill in the time if no time travellers showed up, and they drank the wine and ate the cheese anyway. But yes, we've looked in this sense at least for time travellers, and they have not appeared. Okay, and I for one can say that if I invented a time machine, I'd feel honour bound to go back to that event and say that, so, you know, I'm sure that I'm not going to make it to creating a time machine, at least not one that's going to let me go back and meet those people. Exhibit 2, the grandfather paradox, very well known, technically referred to as a causality violation. I'm sure you've heard some form of the grandfather paradox. The idea is that if you have a time machine, you go back in time, you kill your grandfather, and that, of course, prevents you from being born. Nowadays, with our worldly knowledge of ancestral relationships and so on, people would say it's much safer to kill your grandmother rather than your grandfather, but that's regarded as sort of rather ungentlemanly, and this was thought of a few years ago. But it's been used by science fiction authors. It's a favourite topic. And in particular, Robert Lambourne, a science fiction author whom I used to like a lot when I was a student, sadly died quite a while ago now. But Robert Lambourne wrote some very good time travel stories. one of which was called All You Zombies. I don't know if anybody's ever read that. It's in a collection called The Unpleasant Profession of Jonathan Hogue. All You Zombies is a moderately complicated time travel story, as many of them can be. But in that particular story, I won't go into the details, it would take too long, but with the aid of a time machine and a sex change operation, which was rather racy for the time, the person telling the story manages to be his own mother and father. And the reason the story is titled is that he understands where he came from, but he's very puzzled about how the rest of us got here. He doesn't understand that at all. The Bootstrap Paradox is another such paradox, again the subject of a Robert Lambourne story. This involves entropy violations, and it addresses the issue of where information really comes from. And there are a number of people around nowadays who think that we should be making information the basis of physics. They don't know how to do it, but they have a kind of feeling that that would be a profitable way forward. In one of Hyman's stories called By His Own Bootstraps, it's about a scientist. Let me see if I can get this story exactly right. It's about a scientist who somehow finds himself stranded in a world with aliens. The aliens have dominated the Earth, but they're reasonably friendly aliens, and he thinks that he could win their approval and all sorts of riches if only he could communicate with them. The trouble is he doesn't know how to communicate with them. And then he finds a book which tells him how to translate human language into the alien language. He uses that, he talks, he becomes one of their proteges, has a tremendously successful scientific career, and invents a time machine. And by the end of the story, he writes a book about how to translate the alien language into his language, and he sends it back in time so that he'll find it and be able to talk to the aliens. And you can see the problem. Where did the information in that book really come from? How did it originate? And this is why it's a violation of an entropy principle. I won't go into the thermodynamics of it, but it's an argument against time travel because it allows violations of the ever-increasing amount of entropy in the universe. So these are all regarded as very solid physical reasons for not believing in time travel. And you might think it was natural in view of these, both the observational and the theoretical, that we should rule time travel out. But time travel is not formally ruled out. I think perhaps people regard it as too frivolous to invent a law to stop time travel, but I'll come back to that at the end of the talk. Well, what about time travel in physics? Well, Newtonian physics is very straightforward about time travel. In the case of Newtonian physics, we all travel into the future, but we all travel there at exactly the same rate, whatever we do. Moving around or anything else won't help us to get there any faster. You move through time at a rate of 60 minutes an hour, and so do I, and so our relative velocity, our relative temporal velocity, our speed through time is just 1. Now, special relativity tells us something a little bit different. Great care is needed when interpreting these Einsteinian relationships, but great care has been applied to their interpretation. And in special relativity, time is a relative matter. And this allows for a phenomenon called time dilation. Can I see, I'm sure everybody studies time dilation during their undergraduate course, but are there people here who haven't met time dilation yet in special relativity? No, everybody's beyond the first year stage, you've all done it at least a bit, or maybe even done it in school. Did people do it in school, by the way?
I did a little bit.
Oh, right, okay. Okay. I'm just going to parenthetically say that in schools, people really often annoy me by saying that one of the things that relativity says is that mass increases. Now, I'm a particle physicist, and particle physicists hate the interpretation that mass increases. It's to do with the complex definition of momentum. But I'm very pleased to see that in Turkey, where the school syllabus is a matter of law, that's true in a number of countries around the world, they have a national curriculum and theirs is ordained by law. It's actually illegal to teach people that mass increases. So good for the Turks, that's what I say. If any of you become legislators, introduce that law. It's a very, lots of physicists use it, but it's a very bad way of teaching special relativity and not at all needed. Momentum has a complicated definition, but mass behaves very simply. It's a constant. Okay. Anyway, let me get back to the story I'm trying to tell you. Okay, so this is about time dilation, and the way in which it's usually summarised in a physics lecture is to say that moving clocks run slow. If this were a physics lecture, I'd be much more formal and make sure we knew which reference frames we were talking about and define everything. I'm not going to bother doing that. For those of you who have seen it, you'll know how to do that. But let me just say that the mantra in special relativity is that moving clocks run slow. What's amazing in special relativity is that all moving clocks run slow. So if you and I have identical clocks, and as I'm doing now, I move with constant speed relative to you, because there's a wall, I'm going to turn around and go in the other direction. But if I move at constant speed in a fixed direction relative to you, then according to special relativity, I will find that your clock is running slow as measured by me. I use my clock to make observations, and I find that your clock is running slow. I'm not, by the way, talking about seeing your clock running slow. Seeing is a more complicated process that involves the time lag that it takes light to reach me and so on. I'm saying that if I make observations in which times are recorded using my time system, my clock, by observers at your positions, by data takers at your positions, then it will be the case that measurements will show, that's the act of observation rather than seeing, measurements will show that your clock is running slow relative to me, because according to me, your clocks are moving relative to my clock, and so your clocks will run slow relative to my clock. Now that would be kind of interesting if it was something to do with the mechanics of clocks, but it goes beyond interesting. It is amazing, because in special relativity, if it's true for me that your clocks run slow relative to mine, it must be true for you that my clock is simultaneously running slow relative to yours. So it's not that either one of us has the right clock and the other one is somehow dodgy or invalid. It's that there is a symmetry at work, and each of us will observe the other's clock running slow. Now that's an astonishing statement, because that's a statement about the structure of space and time. That's not to do with the mechanics of clocks, and it's much more amazing. So even the mechanics of clocks explanation would be mildly interesting, at least to an engineer. But to a physicist, the statement that everybody finds that the other observer's clocks are running slow, that's truly astonishing, and you can spend a lifetime thinking about that. Okay, well in special relativity anyway, because of time dilation, I can say, because your clocks are running at a different rate from mine, that time for you runs at a different rate for me. And at low velocities, low speeds, like the ones I've just been talking about, me walking across the room, the difference is negligible. But when we get up to a decent fraction of the speed of light, above about 1/10 of the speed of light or so, this effect becomes bigger and bigger and bigger. And of course, those of you who have heard about special relativity will know that we measure that effect, for instance, when we see high-speed particles, cosmic rays, for instance, coming into the Earth's atmosphere. Primary cosmic rays, which have lots of energy, will often collide in the upper atmosphere and produce showers of secondary particles coming down at high speeds, very close to the speed of light, from the upper atmosphere. Now, many of those particles will be short-lived, and in particular there are particles called muons that are produced in large numbers in these collisions. Okay, the muons are relatively easy to measure. I once did a television program here where we actually took a particle detector up to a cosmic ray observatory in the north of England, and we measured the rate at which muons arrived at the ground, and then we took a helicopter and we hovered over the same site and we measured the average rate at which muons came down through the helicopter. And so we were able to work out the number of muons that decay between the height of the helicopter and the ground station, so we could measure the rate of decay of the muons. And what we were finding was that the lifetime of those muons was much, much greater than the lifetime of similar muons created, as it were, at rest in a laboratory on the Earth. And it was much, much greater because the lifetime, the mean life of those travelling muons, is essentially a moving clock, and because it's moving relative to the clock on the ground or the clock in the helicopter, it's slowed down, and so the lifetime is extended, so the decay rate is extended. That's why we get so many of those muons arriving at the ground. If you're travelling on one of those muons, of course, your clock is not slowed down. If you're travelling on a muon, you're travelling with your own internal clock, and the life is just ticking away. So how does the muon manage to get to the ground if you're riding on the muon? Well, it's because of another relativistic effect which actually shortens the distance between the top of the Earth, the so-called length contraction effect. And so from the point of view of the muon, it's the distance that's shortened. But from the point of view of the observers on the ground, it's the time that's slowed down. Just part of the beautiful symmetry of special relativity. So there is a difference in travel times in special relativity. And we can utilize that if we consider the so-called time travel effect, the twin effect. Time travel and the twin effect. So that's my next topic. And let me briefly talk about that. The idea is very simple. To analyze it properly using special relativity requires 3 frames of reference. It can be done, but it's usually messed up in many descriptions. It's done much too quickly, and people never understand it. There have been ongoing discussions about this for donkey's years. But it's actually, if you find the right sources, very straightforward, very clear, and very illuminating to work it out using space-time diagrams. Okay, now, the time travel, sorry, again, I've used the wrong word. Time travel with the twin effect is very simple. The idea is you take 2 twins, i.e. people of the same age, you stick one in a spacecraft and let them fly off very quickly, in which case, of course, the 2 twins' clocks will move at different rates, but then the space-traveling twin turns around and comes back. We assume that the turnaround is done very quickly, so there's no jiggery-pokery with the turnaround, but coming back means that the twins can meet up. And then, because or one of them at least has gone out and then come back, you can actually see the effect of this different rate of time passage, the different rate at which they've both been going into the future. They've had no control over it, but the rates are different, and they will be of different ages when they return. Now, in the early days of special relativity, some people thought that this must be wrong, and they said, well, but surely, from the point of view of the person on Earth, the twin goes away and comes back, and so the twin on Earth does indeed expect the younger twin, the other twin to be younger, the travelling twin to be younger. But, from the point of view of the travelling twin, he or she just sits in the spacecraft and sees the one on Earth go away and come back. So doesn't symmetry argue that the twin in the spacecraft will expect the one who's remained on Earth to be younger when they meet up? And they can't possibly both expect and find that the other is younger, so special relativity must be complete rubbish. And in the early days of relativity, this was known as the twin paradox for this reason, but it's not really a paradox at all. It's very easy to show in special relativity that the fact that one of these twins, this one, undergoes acceleration means that the space-time path of the younger twin is a, as it were, kinked space-time path. This twin, in technical language, is not an inertial observer and can't be because of the need to accelerate to come back. So it's not that the acceleration, which will just be a short turnaround at the end of the journey, is somehow magically making the twin older. What it means is that there is no symmetry between the 2 twins, so their entire life histories will not show symmetry throughout. So it's the twin paradox that's bunkum, not special relativity. Okay, I won't try to justify that. You're physicists, you can work that out for yourselves. There are a number of good books that do that kind of thing. One of which I might modestly say is written by me, but that's a different story. Okay, now, I want to introduce something which you may or may not have met in special relativity, but which is going to be relevant to the rest of this. I'm going to talk about light cones. Okay, if you throw a pebble in a pond, then you see a bunch of ripples spreading out. And what I could do perhaps is to show you a diagram of that, but instead I'm going to show you one frame, as it were. I'm just going to freeze the outer ripple. So here's a picture in space at a certain time, showing a wavefront where the rippling water has got to as the ripples spread out. I'm only bothered about this outermost ripple. Okay, there it is, as it were, in that last frame. And now let me draw a diagram in which I stack up, this is rather like that foliation space-time we spoke about earlier, let me stack up earlier views of space at different times. I'm going to make the time axis go vertically here, as you can see, and here is the whole of space at some early time, and I throw the stone in, a later time, a later time, a later time, and each time there will be a circle, but the circle, as I go back towards the time when the stone first went in, the circle will have a smaller radius. And if I were to draw this in an appropriate dimensional space-time, what you would see is that these circles really produced a cone for me, a cone showing the motion in a single stationary diagram, but with an extra dimension for time, a space-time diagram. Okay, is everybody happy with that notion of how we're showing motion in a static diagram? You can imagine that in relativity, where we're very concerned about things that happen over time, these space-time diagrams are very useful. And in fact, when I was first introduced to them, it was in a lecture in my own college physical society, given by Roger Penrose, who was then a dashing professor in, if I remember, the University of London, and is now a Professor Emeritus from the University of Oxford and a Knight of the Realm and all that kind of stuff. Penrose, of all the people on Earth, has probably the most fertile geometric imagination of any of us. He is blessed with an extraordinary imagination and has used it to great effect in a long and distinguished career. What Penrose said, I remember, was said that to give his talk, which is not this talk, he had to introduce us to special relativity. So he said, first slide, and that came a picture with all these cones on it. He said, these are light cones, that's special relativity. Next slide. And that was the sort of pace at which he lectured. Okay. So here is a light cone. And what a light cone does is it takes an event, in the language of special relativity. Let's say that event, an event is a happening in time and space. It occupies a point in space and an instant in time. So here it is, somewhere in time and space. Let's let it be a light flash. From that light flash, there will be light spreading out in all directions in a spherical wavefront. I'm not going to try to draw that. I'm going to suppress one of the spatial dimensions. So there's two dimensions of space and one of time. And so what you see representing that expanding sphere of light is a cone. And as we go into the future, the cone gets bigger and bigger, expanding at the speed of light. Everybody happy with that and not too fazed by me suppressing the dimension? Similarly, in the past, we can ask now, from which points, or from which events in the past, which locations in this space-time diagram, might a light flash have sent signals to reach us at the here and now event, this starting event? And the answer is it's the past light cone of the event. So this past light cone is the surface that connects all those events that could have sent a light signal to that event. And this future light cone is all of the events that could have been reached by a signal travelling at the speed of light from that event. Everybody happy with that? So, if we have a space-time, a more particularly a space-time diagram, and we pick out a particular event, about that event we can construct this, light cone structure, and it tells us about signals and their relationship to that event in terms of the speed of light. So inside of this cone we have what's called the absolute future. Here on the cone we have the light cone, where to reach any of those events you have to travel at the speed of light, and outside of it we have what's called elsewhere. And if I want to send a signal from here to this event on the light cone, I have to use something that travels at the speed of light, like a radio signal. If I want to send a signal from here to somewhere inside the light cone, I can use a message written in a bottle or a telephone or something like that. And if I want to send a signal from here to there, then according to special relativity, I'm in bad luck because that's ruled out. It requires faster than the speed of light travel, and special relativity rules that out. And it does so because if we allow it, then we violate causality, and that was something we wanted to preserve. We don't rule out faster than light travel because things get enormously heavy or anything like that. You'll see that sometimes in physics books. It's because they didn't understand the Turkish law. They don't know the things that get heavier. Sometimes they give a more correct interpretation, saying you need an infinite amount of energy to accelerate things up to the speed of light. That is true, but not dreadfully helpful. The real rule comes about because we don't want violations of causality. Okay? Right, well, let's talk about light cones and pathways. If I have my light cone, I have an event here, and I'm going to consider the kinds of pathways in space and time, space-time, that I might take through this event going into the future. So one quite possible pathway is the so-called time-like pathway, and generally we all follow time-like pathways into the future. It's what we do. And if I fire off a photon or something else that travels at the speed of light, then the pathway that the photon travels into the future along will take it along the edge of the light cone, along the light cone itself, and that will be a light-like pathway. And if I watch Star Trek and I see people going faster than the speed of light in the Starship Enterprise, then they are travelling along what we call space-like pathways. And the space-like pathway will enable them to be, as it were, further away from their starting location than even a light ray can manage in a given time. That's what a space-like pathway does for you. We don't think space-like pathways are possible. There have been speculations that there might be faster-than-light particles called tachyons, a name meaning speedy ones, but there's never been any experimental evidence that you can find them. when people commission a new particle accelerator and new detectors, then you always do a tachyon search, but they never come up with anything. That's because we think they're not there. You can find books written about tachyon matter and so on, but as far as we know, that's all fictional. Okay, and there would be real problems in a universe where causality was violated and where this kind of thing was possible. For instance, if we could violate causality, it would mean that we could have some dynamite blowing up before the plunger that detonated it was pressed. Now, all you then have to do is to put the dynamite where the plunger is, and you have a real paradox. You'd be asking yourself, well, why did it blow up? Not only was the plunger not pressed, but it blew up in such a way the plunger's not even there when it blew up. Oh, gosh, it doesn't make any sense. So it becomes a very complicated universe if we allow those kinds of violations. So instead, we prefer to say no faster than light travel in special relativity. Incidentally, there's a whole bunch of things that do go faster than light, but they don't convey information. And so if people make the sort of statement I just carelessly made and say nothing travels faster than light, that's just bad physics, that's wrong. Physics is much clearer than that. There are lots of things that go faster than light, but they're not things that carry information, they're not things that carry signals. And so you have to be very careful when you talk about prohibition on the speed of light. And that's why there's the chance for me to give a 1-hour lecture on things that go faster than light, because a lot of things do. Okay. Now let's talk about space-time and black holes. And this is where these light cones become very useful. So I'm sure you all know about black holes, right? If you have something like a star and it's made dense enough, it can collapse under its own weight. I think things have done that, and they become essentially space-time singularities shielded by a space-time structure that we call an event horizon. Now again, it's the same kind of diagram. There's a dimension of space missing. So these circles really represent spherical structures, and what I'm representing here is what's called a Schwarzschild black hole, a non-rotating black hole. It's got a singularity in the middle, surrounded by a spherical event horizon. And all this stuff outside shows what would happen if I set off little light flashes and watch them develop over time. If I go far enough away from the singularity and set off a light flash, I get a light cone, because in this part of space and time we really don't know about what's going on over there, it's too far away. But if I get closer, gravity will affect the motion of light rays. Light rays don't have any mass, but because gravity doesn't require forces that act on mass, gravity, according to Einstein, depends on space-time geometry. If I get closer, then what will happen is space-time geometry will be distorted by the presence of whatever it is that formed the black hole, and the consequence of that is that the light cone has its axis tipped towards the gravitating source. More than that, the light cone is actually, the geometry can be worked out in detail, it's actually made narrower. And if I go closer and closer, what happens is this tipping becomes more and more exaggerated. So if I fire a little light bulb there, it's tipped very steeply towards here, and when I actually reach the edge of this event horizon, the extent of tipping is so great that the edge of the light cone, the edge that might be expected to, as it were, take the light away from the black hole, is aligned with the event horizon. So it means this light bulb that is just marginally inside can certainly send light inwards towards the singularity. It can try to send light outwards, but the light that it tries to send outwards, the light that out here would be going outwards here, is so affected by gravity that it ends up going essentially parallel to the event horizon. So it doesn't make any outward progress. And that's why the event horizon of a black hole is a light-trapping surface, why we don't, in classical physics, expect anything to come out through the event horizon of a black hole. Are people happy with that? People looking a little bit puzzled. I'm kind of assuming this generation will know quite a lot about black holes and that stuff. But everybody's happy with those statements. Okay, good. Now let's get to time travel and general relativity, because this is where the shock starts. Now what happens in general relativity is that, although it's not present in many of the ordinary solutions, you can find situations in general relativity, solutions to the Einstein field equations, which are at the root of general relativity, that actually allow for situations like this. You can find a closed loop that is time-like at every point. So time-like path through space-time is exactly the kind of path that we normally expect things to follow in relativistic physics, be it special or general relativity. But in general relativity, there are mathematical solutions to the Einstein field equations in which those everywhere time-like paths close up on themselves. Now, think of what that would mean. An observer following such a pathway can just go on following it as time passes. You can repeat history again and again and again. So, if you're at some point on this time-like pathway, and because it's time-like, you have a good idea of what's the future and what's the past, you, by travelling into the future, are destined to revisit your past. And according to this picture, you revisit it exactly. You wouldn't say, oh my goodness, here I am again, unless you said that the last time you went round. It would be an exact repetition of the events in a history that was a cyclical history. Now, I don't know whether slight perturbations could be introduced so that you could say, oh, I'm nearly here again. Well, that's great, I'm going through time several times in my own lifetime. That would be very weird. But you can see that it's worrying that general relativity allows this at all. I mentioned that I was at the meeting, in the Nelson meeting of the New Zealand Institute of Physics last weekend, and a New Zealander, not in this department, but in another New Zealand department, who is well known for his work on general relativity, was one of the speakers there, and somebody raised the issue of closed time-like curves. And he kind of looked, I thought, a little bit shifty. This is a man, by the way, who's written about wormholes and so on, which I'll get to in a moment. He looked a little bit shifty and said, we don't even want to go there. And I thought, well, I'd quite like to go there. I think it's fascinating. But technically, it's scary stuff, I think, even for the experts. Worse, back in 1937, a man called von Stockham at the University of Edinburgh discovered a solution to the Einstein field equations. Not a very realistic solution. It involved an infinitely long cylinder of dust. But in general relativity, you're grateful for any solution you can find. He found a solution to the Einstein field equations involving an infinitely long rotating cylinder of pressure-free dust. And what he found was that all you really had to do was to orbit that cylinder. It was a rotating cylinder, I should say, and this department is famous for the work of Professor Kerr, who did stuff about rotating black holes back in the 1960s. But this is different. This is 1937. Von Stockham, an infinitely long rotating cylinder of dust, and he showed that around it there would be closed time-like paths. Paths that physically one could follow, but which would enable the observer to repeat their life experiences endlessly. Extraordinary. And of course, this makes many people say, well, is general relativity right? We test it as far as we can, and as far as we can, it's worked very well. But can a theory that allows this kind of thing to happen be a reliable theory? And it may be that it's not. It may be that this is the solution. Perhaps there is some principle in general relativity we don't know, or maybe we need an additional law that says if we get solutions like this, we don't allow them anyway, just like we rule out faster than light travel in special relativity. Or maybe there is some new theory that we need. And many people, as you may know, are in the process of research into quantum gravity, especially through string theory, to see whether they can combine general relativity and quantum physics to come up with a revised and extended theory that would be the next chapter in this story of theoretical developments. But it's scary that general relativity allows this. This brings me on to wormholes. Now, wormholes are another surprising class of solutions, and the man who was speaking at this institute meeting was actually the author of a book on Lorentzian wormholes, which I've had on my bookshelves for many years. So he's written about all these. They were known about fairly early in the history of general relativity. And the idea is often expressed by diagrams like this. You take a chunk of space-time, suppressing dimensions as appropriate, bend it around and create, as it were, a shortcut through space-time. And there are lots of science fiction stories that make use of that. Some of them even explore the possibility that when you do this, you find that it takes you longer to go through the shortcut than it does to go around the long way. And there are some great science fiction stories about people trapped in wormholes who thought they were going somewhere fast and find they're just throwing their lives away. In Star Trek Deep Space Nine, when they ran into diminishing plot adventures, they invented a wormhole near to Deep Space Nine, and greatly improved the series because people could then go through the wormhole and have all sorts of adventures, and even adventures inside the wormhole. But that was science fiction, so they tell me. Here's a picture from Scientific American, so it must be true, showing a wormhole in Times Square. And as you can see, this was their notion of how it might be in the future, when you'll have wormhole connections to the American desert. So, you know, you can come out of your office and be straight at your desert home in Arizona in practically no time at all, thanks to the local wormhole. I think that's a really nice idea. I love that. But wormholes have been investigated scientifically, and some surprising things emerged from them. Now, in 1986, or until 1986, it was thought that wormholes were unstable. Although you could find the solutions to the Einstein field equation, it was believed, and still is really, that they are unstable and will collapse, and they will collapse rather quickly, which is a pleasing thing to many people. But then Carl Sagan, who was planning to make a movie about aliens, contacted Kip Thorne. Kip Thorne is a very distinguished relativist at the California Institute of Technology, and said that he wanted a plausible way of allowing people to travel through space at high speeds and so on. And he'd heard about wormholes in general relativity, and could Thorne tell me if this was okay? And Thorne said, you know, knew about these things too, said yes, and became a bit interested and investigated it. And then realised that wormholes, if they existed, would make time travel possible. And so this is all going to connect back to time machines. Now what happened was that, firstly, it was known that you could keep these wormholes open if you were a sufficiently advanced civilization, maybe, by threading them with what's called exotic matter with negative pressure. This is a bit like dark energy that we sometimes discuss. There's not yet any agreement amongst scientists whether this is a real possibility to create this exotic matter. We know of things that do create negative pressure, but not very much, as it were. Okay, so anyway, it became a real possibility to talk about these things, but not necessarily a likely one, and that's still a matter of debate amongst the experts. But what Thorne realised, and wrote a paper in PhysRev with his students, not PhysRev, I'm sorry, it was published in American Journal of Physics initially. He wrote a paper with students about was this: if you take one end of a wormhole and you stick it on board a ship, a spaceship, and you fly it away at high speed and then you fly it back, it will come back a different age from the other end. And so you now have a time machine. And what you can do is jump in one end of this wormhole, the later end, and come out earlier from the short distance that you've travelled through, and go back and shake your own hand. And you know, after a few of these trips, you could have a breakfast party with yourself, and after a lot of these trips, you'd be an army. So suddenly time travel is possible as long as the wormhole exists and has already gone through this time dilation effect, this twin effect that changes the ages of the two ends. And Kip Thorne wrote a book about this called Einstein's Outrageous Legacy, in which he has some nice things about people kind of holding hands while they take the wormhole out and bring it back to work out what really goes on and the problems that ensue. But that's a science book, not a science fiction book. Now, of course, what this means is that in general relativity, there is the possibility of Doctor Who-like time travel, provided we use a wormhole. Whether wormholes really exist is the issue, but if they do, if they do, okay, then I hope we will have the decency to build our time-travelling capsules in this form, because I think anybody who knows Doctor Who out of just simple respect for the Doctor should always build a machine to look like that. So if you ever do construct a time machine, make sure you paint it the right way. Okay, well, time travel seems to be possible in general relativity if these wormholes exist and can be stabilised, but that raises the question of where we get them from. And to answer that, I'm going to call on quantum physics. Quantum physics supplies our deepest insights into the nature of microscopic particles, fundamental forces, and so on. And it uses probability in an unavoidable way. I won't go through all this stuff because you're physicists, and if you don't know about the Copenhagen interpretation yet, and unconventional interpretations like the many worlds interpretation, then you will meet those things in due course. But there are ways of dealing with the probabilities that arise in quantum mechanics. The conventional one is to say that there's only one universe, and that wave functions, which will mean collapse, they undergo a strange process, and lots of physicists, although they use that, don't really believe it. There are more sophisticated versions of that around now, like consistent histories, which will take me even longer to explain. But the many worlds interpretation is easy to understand. It says that basically all the probabilities that we work out in quantum mechanics arise because there are many different versions of the universe. And whenever we have a process that might, according to quantum mechanics, happen in a number of different ways, each with a calculable probability, what's actually happening is that our universe is splitting, and we're getting more and more copies of the universe, and it's splitting in the ratio of the probabilities that we calculate. So the many worlds interpretation, despite its rather playful name, is an incredible interpretation. But some physicists accept it because they think that the problem of understanding the quantum physics of measuring devices, which underlies the conventional Copenhagen interpretation, is such a deep and irreconcilable problem in conventional quantum mechanics that it cannot be made to work without this kind of assumption. And they don't care about the profligacy of universes. The Nobel Prize winner Abdus Salam said, "Nature is profligate with structures, it's conservative with principles." And these are just structures, so some physicists are happy to just let the universe multiply. It's the principles they care about. Now, if this was the kind of branching universe we lived in, it would get over some of the objections that we had to time travelers. Suppose we did have wormholes, suppose they were creatable using quantum physics, and suppose it was this kind of universe. Then some people have argued what would happen is that when you went on a time trip into the past, you wouldn't know with your wormhole time machine which of the parallel branches of the universe you were winding up on. So when you actually shot your grandfather or your grandmother, it was actually somebody else's grandfather or grandmother in another branch of the universe. And so in this kind of branching quantum universe, then maybe everything's possible. How do we get it? Well, we get it by going down to the Planck scale, where quantum gravity gets confused, where quantum effects get confused with gravitational effects. And there we think there's a seething quantum reality or non-reality of virtual black holes and wormholes coming in and out of existence. And all we need is a sufficiently advanced technology to grab one of those little wormholes, blow it up enormously so that it becomes macroscopic, and then we can shove our police telephone box through it in order to give us a time machine. So as you can see, everything's worked out. It's only a problem for engineers from here on. I've done the hard bit. From here on, it's straightforward. I'm sorry, I'm overrunning my time. Can I go on for a couple more minutes? Is that okay? Maybe as a right. According to quantum physics, the physical vacuum is seething with activity at the quantum level, since there's always some probability of the appearance of short-lived particle-antiparticle pairs. Now, Stephen Hawking, who has now retired, but was until recently the Lucasian professor of mathematics, applied mathematics in natural philosophy in Cambridge, so he holds, or used to hold the chair that Newton held. That position is now occupied by Mike Green, a string theorist. Hawking was rather worried by this, and he suggested that in the presence of a time machine, what will happen is quantum fluctuations will occur in the vacuum, that energy will, as it were, flow through, and I said that you could have a nice breakfast party or even become an army. Well, he said, if you created a time machine, what he thought would happen, he's moved himself back from this position now, but he argued at one stage, if you created a time machine, what would happen is because of these quantum fluctuations, inevitably, energy would flow through, but it wouldn't do it just once, it would do it time and time and time again. It would magnify itself, it would avalanche, and create so much energy that the space-time structure would collapse, and the time machine would rule itself out of existence. So as you tried to take one of these quantum wormholes and blow it up, you'd find the thing was automatically unstable for good physical reasons. Now, I think that's a really neat argument. That's not just, oh, I don't like time travel, let's rule it out. It's, when we create time machines, this is what will happen. There will be an avalanche of energy, and they'll destroy themselves. Now, that's a physicist's thinking. As I say, he's actually moved back a bit from that, but he introduced this idea of what's called chronology protection. As he said at the time, he was trying to create a future safe for historians. And he says things with great difficulty. You may know he can't talk. He's not been able to speak for many years. He has a voice synthesizer, and with a little bit of motion in one hand, he programs with great labour this thing. But even so, he writes papers on general relativity, books and so on. And has been an enormous inspiration to many. So it may be that quantum physics comes to our salvation, and that it actually saves us from time machines and makes the world safe for historians. Now, I'm going to end by going one step beyond this to Niven's law. Larry Niven is a science fiction writer who whom I was very fond of. His later books were pretty rubbishy, but his early ones were all rather good. And he came up with, I thought, a very good argument about why we don't find time travelers. Now, this is science fiction rather than science, but again, I think it's physicists thinking at work. He never completed a physics degree, but he started a mathematics degree and took some physics while at college. And this is what he said: if travelling into the past is possible, it still won't happen, because we will tamper with the past until we create a stable future. And by stable future, that's one in which time travel is never invented. So at last we have the reason why all those time travellers never showed up at the MIT gathering. It wasn't because they weren't fond of cheese or wine, it's because they went back, they fiddled with the past. I don't know what they did, but they changed it in such a way that, very sadly for all of us, time travel will never be invented. So we're in a very stable universe, but not one that will any longer have time machines in it. Thanks very much. I've overrun my time, so please feel free to go. If anybody wants to ask me questions, I'm going to be too happy to answer, if I can.
Any questions?
Well, I've got one, but it's pretty unrelated. It's more a question to you as opposed to your lecture. What's actually in those police boxes?
Well, I never got to be inside one of them. I actually saw the original Doctor Who one, because when I was a schoolboy, I was taken on a tour of the BBC, and I saw the control panel for the original TARDIS, and I saw the Doctor Who telephone box, as well as lots of other things at the BBC. And I have to tell you that the control panel for the TARDIS was basically made out of plywood with a few old meters in it, and close up it was really ropey. But inside the real police telephone boxes, there was basically just a telephone. The idea was the policemen could go in there and simply contact their stations. Before, they all had personal radios and so on. So, it was an essential way to let policemen contact their headquarters. They had other uses, I think, but that was the basic purpose of it. So, there was no number to dial, you just contacted the police station. That was it.
Sweet, thanks.
Okay, if there's nothing else, if anybody does come up with any good questions about, or even bad questions, any questions at all about time travel, please feel free to stop me when you see me and ask, and I'm sure I'll find some way of wriggling out of it. Unlikely to know the answer, but it's been a pleasure to talk to you about this subject. Thank you.
Okay.